Actually, I think most people didn't have trouble. So probably if you ask the person next to you, they can help you also. So everybody got my email, right? So by now, due today, you should have registered for the forum, and you should have either sent me a bio and a photo, or tell me that you're not going to send one. And you should also have access to the homework. So that's been posted already. I sent it by email also, and the syllabus. So if you guys have any questions about that, maybe at the end of class we can talk a little bit about it. But I think that's it. So okay, so let me just finish where I think I got to tell you guys this, but then the camera cut me off. So I was talking about the d-dimensional cross polytope, and I said that we could describe it either as the convex hull of plus and minus the unit vectors, but we could also describe it as the points in RD. Did I write this, by the way? I forget.
You got A element left brackets and cut off.
Okay. So anyway, so we can also describe this as the points in RD such that AX is less than or equal to 1 for all A in 1 and minus 1 to the D. Okay. How are you supposed to interpret this? You might interpret it as dot product. Or if you are used to dual spaces, then you should think of A as living in the dual space, and this is a linear function of X. Okay. And I'll say more about that later on. But anyway, so that's the description. And I just wanted to point out to you that I can also write this as this system of inequalities, okay? And I can write it in matrix form. So what this means is that x1 plus x2 plus x3 is less than or equal to 1, and so on, okay? So when I write an inequality of matrices, then implicitly the matrices should be of the same shape, and what I'm saying is that they're coordinate-wise less than or equal to each other. Okay? So that's the hypersimplex. Sorry, the cross polytope. Okay? Any questions about it? This is the three-dimensional one, but then there's a d-dimensional one in every dimension. Okay? Any questions about it? And again, let me make the point that this isn't supposed to be obvious that these two descriptions are equal to each other. As you saw in the homework, you're supposed to do this for the cube. And it would be a good exercise for you to do it for this. Actually, I had it as a homework problem also, but I decided to go easy on you guys and just give you one of them. But this is an equality that is not obvious. Okay, it's a good exercise. And I'll prove this later on in class. Okay. So these are some examples of polytopes, and I want to talk about more examples of polytopes. Other constructions of polytopes. So there's intersection. Okay. So if you have two polytopes P and Q in d-dimensional space, then you can just take their intersection, and you know what that means. So this is P. And this is Q. Then we're just considering the intersection, right? And I think it's probably intuitively clear to you guys that this is a polytope, but you have to prove it. And this is one of your homework problems, is to prove that this is a polytope. And it's a polytope in RD. Okay. So that's one way of building up new polytopes from old polytopes, is just intersecting. Okay. Another construction that we can do is what is called Minkowski sum. So it's a way of adding polytopes. So again, if you have two polytopes in the same space Rd, then we can form the Minkowski sum. And this is going to be the set of points of the form P plus Q, such that point P is in my first polytope and point Q is in my second polytope. Okay? And this also lives in R to the D, right? Okay. Oh, sorry. Thank you. P is in P and Q is in Q. Okay? And again, it's a homework exercise to prove that this is a polytope. But what I want to do is I want to give you an intuition of what this actually looks like. So this I have to do carefully. So let's say that I have this P, and I want to take the Minkowski sum with this Q. Okay. So this is fun. This is actually a fun thing to do. Because what you're going to do is basically you're going to say, okay, well, I'm supposed to take every point in here and every point in here and add them in every possible way and see what I get. So the way you do this is you say, okay, let me fix a point in P and see what happens if I fix that point and I add it up with all the points of Q. What am I going to get? It's just a triangle corresponding to this point. Okay. So just imagine that here's my P. Okay. And then corresponding to this point, I'm going to get a triangle's worth of points in P plus Q. Okay. But I'm supposed to do this for every single point in P. Okay. So for example, let's move up P. So for example, here I'm also supposed to get a triangle's worth, and that triangle is going to be kind of the same but a little bit higher. Okay. And then I keep moving up, and so on, until I get to the top. Okay. And so all of these points are in P plus Q. So far what I did is that I traced this part of P. Okay. Now let's start tracing over in this direction. Okay. So then when I start moving in this direction, then my triangle is going to start moving to the right. Okay. So I get something like this. Okay. And now I'm in this plus Q. Okay. Now let's move down in this direction. So then what that's going to do is going to bring my triangle down. So I get something like this. Okay. And then as I bring the point back in here, then I'm going to get a bunch of triangles like this. Okay. And this is something that you might want to replay the video for if you lost track of what I did, because now it just looks like a mess, right? But again, what you should be thinking is that basically you're kind of, for each point in P, you're putting a little triangle, and then you're letting that triangle move around. So you have like a square's worth of triangles, and then when you put them all together, they form this shape that looks nice and polytopal. Okay? In this case, what we get is this. Okay? That's the sum of the triangle and the square. Okay.
What if the triangle would fit completely in P though? Then you would make custom. Yeah, so you did it only on the border of P.
So what I meant actually is for this triangle to fit inside P. So this triangle was meant to be exactly half of the square. Okay. So then the first one fits inside P, but then as you move it around, you get a bigger shape.
Right, but Nick asked if you just took it and traced it only around the border of P.
Oh, I see.
But that's maybe not enough.
So let me repeat the question actually. So next question was whether I can just trace the border and forget about the inside. And then the answer to that is that, well, if you do that, then you will have traced the border of this, but you might have missed some points in the inside. So you can imagine if this square was very large and Q was very small, I think this is what you're telling me, then what you would get is some kind of ring with a hole in the middle. So you actually need to trace through all of P. But when it comes to drawing the picture, actually,
If you're looking at, this is continuous space, right? An integer lattice. So
Mhm.
take Q across every point. It's gonna fill any interior or any exterior shape you make.
so
I mean, I guess what I'm trying to say is we can assume that it's gonna fill in on the interior. We only need to really look at the exterior shape and assume that the interior is going to fill.
So you're right. Basically, you're going to prove a theorem that says that actually this is a polytope. And so once you know it's a polytope, then you know that the Minkowski sum is not going to be a ring because a ring is not a polytope. So you are right that for effectively doing this, actually you only need to go around the border and just fill in the inside because it's going to be a polytope. And if you think about it a little bit harder, you'll see that actually all you need to do it is for the vertices. Okay? But anyway, so that's one operation, Minkowski sum, and we'll see why this is a very important operation. Okay? And this is an operation that I really encourage you to just draw some pictures, okay? Because it's one thing is to see somebody do it, and another thing is to do it yourself. So you just pick two polygons and do the Minkowski sum, and just go ahead and do it. I think it's important practice. Okay, so that's another way of building up a bunch of polytopes. If you have all polytopes, you can take their Minkowski sum and get other polytopes. The other thing you can do is that you can multiply polytopes. So if you have, and here we're going to have two polytopes that live in maybe different dimensions in R to the D and R to the E. And what we're going to consider is the product polytope. And this is going to consist of all things of the form like this, PQ, where P is a point in my polytope P, and Q is a point in my polytope E. My polytope Q, sorry. So I should say some things of the form like this, where P is in P and Q is in Q. Okay. So let's think about this for a second. What do the points of P look like? Well, we're in D dimensions, so we can think of them as column vectors of length D. That's what P looks like. And points in Q look like column vectors of length E. Okay? And so what I'm saying is you should take the column vector of length D that represents a point in P and the column vector of length E that represents a point in Q and just put them on top of each other, and you're going to get something that has length D plus E. Okay? So this thing lives inside R to the D plus E. And what I claim is that when you do this, you get a polytope, and this is another one of your homework problems to prove that this is a polytope. By the way, you're going to have some more tools to show that these things are polytopes. Right now, maybe these exercises seem very difficult. You'll have tools to show this. Okay? With your bare hands, it's kind of hard. But you'll prove that this is a polytope. Okay? And again, what I want to do for now is just show you how you would draw this. Okay? So let's say that you want to take the direct product of this polytope and let's say this polytope. Okay. So the way that you can do this is that you can draw your polytope P, and then on each vertex of P, you're going to draw a copy of Q hanging from there. Okay. So here you're going to draw a copy of Q. Here you're going to draw a copy of Q. here you're going to draw a copy of Q. Okay, one on each vertex. And if you do this, you'll see that actually there's some copies of P that I haven't drawn in. Right? So here's a P, but also if you see that it's very natural to also consider this copy of P. So you just connect the corresponding vertices of the blue polytope, and they're going to form the shape of P. And that is a polytope. That is the polytope P times Q. Does that look like a polytope to you? It's a little bit hard to parse because, think about it, this guy lives in 2 dimensions, this guy lives in 2 dimensions, and so this lives in 2 plus 2 dimensions. It's a 4-dimensional thing, and that's why it looks so strange. You can't really see it look 3-dimensional because it's not 3-dimensional. It doesn't fit in 3 dimensions. This thing lives in R to the 4. Okay? And you should really think that black and blue live in completely complementary dimensions. Okay, so you have kind of a 2-dimensional plane that's like the black plane. You have a 2-dimensional plane that's the blue plane. And the thing about 4 dimensions is that you can fit 2 2-dimensional planes that only intersect at the origin. Right? Because in 4 dimensions you have 4 degrees of freedom, you have 4 axes. And so you could take the first 2 axes and make a plane, a black plane, take the other 2 axes and make a blue plane, and the intersection of those planes is just the origin. And so it is very misleading to think that black and blue are crossing here because they live in complementary dimensions. But, my board is 2-dimensional, so this is the best that I can give you. But that's a picture. Okay? And again, I would really encourage you to just take 2 polygons and multiply them, and you're going to get a 4-dimensional polygon. And it's very important to get a good practice to do that. Okay. By the way, let me make a comment about this, about drawing, okay? Because I've actually talked to a couple of you already who have told me that you're not very good at drawing polytopes. Okay? And I'll break it to you. I actually was not very good at drawing polytopes, and now I'm very proud that I can do things like this because it took me a lot of hard work, okay? And that's why you're here. You're here in a class where we're going to talk about polytopes, and you're going to practice drawing them, because nobody's good at them. Nobody's good at drawing polytopes until you draw a bunch of polytopes. And I reserve the right to assign homework that says draw this polytope, and if I don't like it, I'm gonna mark it off. Okay? And I should tell you, I always carry around now that I'm teaching this class. Oh, I left it upstairs. I'm lying. Anyway, I always carry a grid paper, and so should you. If you're in this class, you should always carry a grid paper. It's going to help you draw. Okay? But you will get good at drawing these things. I should tell you, when I was in high school, I wanted to be an architect, and then I took this class on sketching, on what do you call this class in English? It's like drafting. Okay? And I just could not draft and not make a mess with the ink because we had to use I don't know if it's called Chinese ink in English also. Spanish is, I'm sorry? Calligraphy ink. Okay? And I would always make a mess, and I thought, I'm no good at being an architect. I can't draw. And then that's why I'm not an architect. Okay? So I don't want you guys to not be discrete geometers just because you can't draw pictures. Okay? So I'm going to make you practice. Okay? I think my drafting teacher should have been tougher on me. Okay, so these are 3 constructions of polytopes, and this gives us ways of constructing some polytopes from other polytopes. One observation is that, let me just make a quick observation here, is that from this point of view, it's easy to describe the d-dimensional cube as just being a product of 1-dimensional cubes. Okay, this is just C1 times C1 times C1 d times. this is something that you have to kind of stare at the definitions long enough that you see this. If I write a proof, it's not very useful. You just stare at the definitions and you will see that this is true. Okay. But so that gives us some examples of polytopes. So now maybe we know a little bit more what we're talking about. But you guys have to start proving things, and so we need some tools. And we don't have a lot of tools yet. And so that's what I want to do for the rest of the class. So what I want to discuss next is how in the examples that I showed you of simplex, cube, and cross polytope, for each one I gave you two descriptions. One description was as the convex hull of something, and another description was as the set of points satisfying some inequalities. And what we're going to talk about next is how any polytope always has those two ways of describing it. We always have a way of describing it like this, and a way of describing it like this. So this is what we call the V and H descriptions of polytopes. So the point is that we have described polytopes in two ways, as convex hulls or and so this is called, so when we describe a polytope as a convex hull, then this is called the V description. And the reason for V is that we're talking about the vertices, right? Basically, when I tell you that the cross polytope is described like this, I'm telling you that these are the vertices, plus and minus the unit vectors. So this is the vertex description. Okay. Or I've also described it as inequalities. Like we have over here. Okay. And this is called the H description, because whenever we have an inequality, we are describing a half space. Okay. So that's what H stands for. Stands for is half spaces. Okay. And let me say something very basic, very obvious, but extremely important. And so I need this to be clear to you guys. Whenever I write a linear inequality, like, I don't know, 3x plus 4y minus z greater than or equal to 2, whenever I write something like this, and let's say that we're in 3 dimensions, so this is R3, what are we describing here? Well, if we had an equality, then you guys know that what that describes is a two-dimensional plane. Two-dimensional plane. That's if we had the equality. The equality would be describing the plane, but we're describing an inequality, okay? And the point is that whenever you have a plane, a two-plane in 3 dimensions, then that plane always cuts the space into one side and another side. The side where you have greater than or equal, the side where you have less than or equal. And you might notice that this is very important then that we have something like the reals where order exists. If we start looking at trying to do this in the complex numbers, then we're going to run into a lot of trouble because there's no less than or equal to in complex numbers. So the theory of polytopes for complex numbers is much harder. But we're in the reals, and so when I write something like this, I'm saying, you know, here's that plane, and when I have a greater than or equal to, I'm describing a half space. So again, very basic idea, but extremely important. And so I want to make sure that it's very clear to you guys because we're going to go over and over and over. This we're going to need all the time. Okay? And so this is the point. When I describe an inequality, I describe a half space. And so what I'm doing when I do something like this, when I write these 1, 2, 3, 4, 5, 6, 7, 8 inequalities, I'm describing 8 half spaces. And I'm saying if you want to cut out your polytope, then you need to say, you know, here's a half space, and you need to be on this side of that half space. Here's a half space, and you need to be on this side of that half space, and so on. And you see that there's 8 two-dimensional faces of this guy, which is why I need 8 inequalities, and that's why this is called the half space description. Okay? And so the point is that we can always do this. So then let me state the main theorem for polytopes. And when I say main, I don't mean the main theorem of today's class. I basically mean the main theorem of this course. Okay? The thing we're going to be using the most is that the convex halls of finitely many points are the same things. So this is how we define polytopes, as a convex hall of finitely many points. But that's the same thing as the bounded intersections of half spaces, of finitely many half spaces. Thank you. Okay? And so this is what we call polytopes. Right? So this is definition, but this equality is the content of the main theorem. And this theorem is something that is probably fairly intuitive to you guys, at least in 2 and 3 dimensions, but we need to prove it. Okay? And that's our next goal, is to prove this. I'm going to give you a sketch of the proof. If you want to read all the details, they're all in the book. But I want to basically give you just an idea of all the main features of the proof. Okay? So let me make some temporary definitions. What I mean by temporary is that they are definitions for this proof, and once we finish proving this, they will be unnecessary. So let me define an H polyhedron to be something of the form, and I denoted P of AZ, and is basically something described like this, like half spaces. X in Rd such that AX less than or equal to Z. Okay, so here A is some n by d matrix, and Z is a column vector of length n. So whenever I write something like this, you should be thinking, actually let me move over so the camera comes with me. Whenever you see something like this, you should be thinking that we have something like this. This is something like AX less than or equal to Z. It's the explicit inequality description of a polytope. And there's a bit of a lag with this camera, so I need to stay here for a bit, because it'll come eventually. So that's what we call an H polyhedron. Okay. Maybe it's not going to come. Okay. So what about a V polyhedron? Well, I would like to say that a V polyhedron is basically a convex hull. But there is an issue with this, which is that if you look at the definition of an H polyhedron, this thing can be infinite. It can be unbounded. If you just write down some inequalities, there's no reason to expect that this should be bounded. For example, if you say x greater than 0, y greater than 0, z greater than 0, you have the positive orthant, which is not bounded. And so we need to make a definition of V polyhedron, which is kind of like a vertex description of a polytope, but it allows for infinite things. Okay? And so I'll say what this is in a second. But let me define what a cone is. So when I say something like cone of a bunch of vectors, what I mean is let's say that we're in R2, so here I have a bunch of vectors, W1, W2, W3, and the cone is basically going to be what you think of as the cone starting at the origin and going out to these guys. Okay? So it's basically this thing over here. And what is that? Well, if you look at this ray of the cone, it's the positive multiples of W1. These are the positive multiples of W2. Basically, we're allowed to take positive multiples of each one of our vectors and then add them up. So this is just everything that we can write in the form sum of lambda I Wi, where the lambda i's are greater than or equal to 0. Okay? And they don't need to add up to 1. They could be just any positive, any non-negative numbers. Okay, so that's a cone. And now, the next thing that I would like to point out to you is the following. That if you take, for example, the Minkowski sum of, let's say this. So if you take the Minkowski sum of this triangle, or maybe I'll make it a little bit more complicated than that. Let's say that it's this triangle. Okay? And I take the Minkowski sum of that with a cone. Then what am I going to get? Well, basically, at each one of these points, you can have that cone. So you're sliding that cone around. And so if you look at what you're going to get, you're going to get something that looks like this. Okay. I'm doing this quickly because I have practice. If you don't see this right away, you should draw it. Okay. And you see that this is exactly the kind of possibly unbounded thing that we are after. Okay? It can be unbounded, but it might have some kind of vertex-looking stuff over here. Okay? And so this is what I want to do. I want to define a B-polyhedron to be a Minkowski sum of a polytope and a cone. Okay? So this is anything of the form convex hull of a bunch of vertices, Minkowski sum with a cone of some other vertices. Okay? And so what I'm doing is that I'm describing this set by saying what are the vertices of this polytope and what are the rays of this cone. Okay?
So we allow the empty cone?
We allow the empty cone. That's right. Well, rather than empty, we probably want to think of it as the zero cone that only has the origin. Because if this is empty, then we don't have a Minkowski sum. Right? Okay, so that's an H polyhedron, that's a V polyhedron. These are two ways of describing this kind of thing. Okay? And of course, the point is that they're the same thing. So what I have there is my main theorem for polytopes, and what I'm going to write here is the main theorem for polyhedra. Which is that these two definitions describe exactly the same thing. H polyhedra are the same thing as V polyhedra. So anything that you can describe in terms of inequalities is also a Minkowski sum of a polytope and a cone, and vice versa. Okay? And let me just give you a sketch of the proof. So what I'm going to do is basically tell you, if you have an inequality description, how do you turn it into a vertex description? And if you have a vertex description, how do you turn it into an inequality description? That's the idea. Okay? And I think today I'm only going to have time to do one of the directions. I'm going to do this direction. So I'm going to show that every V polyhedron is an H polyhedron. Okay. So let's consider any V polyhedron. Okay. So there's my V polyhedron, and what I want to do is describe it in terms of inequalities. So first, let's write out explicitly what this means. Okay. So what are the points that live in P? Well, they are the points such that they can be expressed as something here plus something here, right? Now, what is something here? Well, something here is a linear combination of V, right? So in other words, I should have lambda 1 up to lambda n such that, let me write it like this. Actually, let me just do it in 2 steps. X in Rd such that there exists V in the convex hull of V and Y in the cone of Y such that X equals V plus Y. Okay. That's what it means to be in the Minkowski sum. Now, what does it mean for V to be in the convex hull of V? Well, it means that we can find lambda 1 up to lambda n such that the sum of the lambda i's is 1 and the lambda i's are greater than or equal to 0. And V should be basically the linear combination lambda 1 v1 up to lambda n vn, which we wrote as V times lambda. Okay. So the lambdas are the coefficients of V. And what does it mean to be in the cone of Y? Well, it means that we can find mu's, let's say mu1 up to mu m. Now, there's no condition on the sum of the mu's. They should just be greater than or equal to 0. And Y should be a linear combination of the vectors in Y. So we write it like this. And so what I'm saying here is that X can be written as a linear combination of the vectors in V, which are the vertices of the polytope, and the vectors in Y, which are the rays of the cone. Okay. All the coefficients are greater than or equal to 0, and the lambdas add up to 1. Good so far? This is just definitions. Okay, so now what I'm going to do is that I'm going to say the following thing. Define a polytope Q, and Q is going to be the set of vectors of the form x lambda mu. So x has length d, lambda has length n, and mu has length m, such that x equals v lambda plus y mu, and sum of the lambdas is equal to 1, and the lambdas are greater than 0, and mu's are greater than or equal to 0. So in other words, I'm taking this guy and I'm just getting rid of the qualifier and making a bigger set out of it. So what am I doing here? Let's see. the picture that you should have in mind here is this, that we have some polytope P that lives here in R to the D. Okay, this is P. Okay, but we have built something in a bigger space. Okay, so thinking that here there's a bigger space, R to the D plus N plus M. Okay, in a sense, we're thinking that this is the space of all possible x's, right? R to the D, whereas this is the set of all possible x's, lambdas, and mu's. Okay? And so Q is some polytope that lives here. Maybe, it probably has more dimensions. There's Q. Okay? But what I want to point out to you is that if we consider the projection of the big space into the small space that forgets the last m plus n coordinates, okay, so I'm saying consider the projection map that maps x, lambda, and mu to x. Okay. Where does Q go? Well, it goes exactly to P. Okay? Because if you have something in Q, then when you map it to P, you get exactly the same thing, and there exists these lambdas and mu's. Okay? And conversely, if you have a point in P, that means that there exist lambda and mu that satisfy the necessary equations, which means that there is a way of listing that point P into a point X with a lambda and a mu. Okay? And so the point is that the projection of Q is P. Okay? So let me summarize what I've said so far. I'm defining some strange polytope Q. Note that Q is, well, one thing that you should note is that Q is an H polyhedron. Okay? Why is Q an H polyhedron? Because it's the set of points satisfying some inequalities. There's one thing that you should realize, which is that whenever you have a linear equation, you can think of it as an inequality, right? If A is equal to B, you can think of it as A bigger than or equal to B, A less than or equal to B. Okay? So you can think of equalities as just a pair of inequalities. And that means that I'm describing the set Q only in terms of inequalities. Is that point clear? For example, if I want to say this equality, I would just say sum of lambda is less than or equal to 1, sum of lambda is bigger than or equal to 1. If you satisfy both, you have to be equal. So this set is described only in terms of inequalities. Okay? So that's what we call an H polyhedron. Okay? And P is a projection of Q. Yeah, question?
So it's, I mean, P is bounded, right? It's your convex whole of D. Q is therefore not necessarily bounded in the Q directions. Right? It is bounded over.
So the question is about boundedness, and actually you'll realize that I just drew P to be bounded so that it would be easier to draw. But P doesn't even have to be bounded because P is the Minkowski sum of a bounded thing plus a thing that is possibly unbounded. P is everything, and so this might be a very unbounded picture. P might be unbounded, Q might be unbounded. Q is, I think, almost surely unbounded. Yeah, Q is always unbounded. So this is some kind of schematic picture, but there is unboundedness in this picture that I'm not drawing accurately. Okay? But what's the point? The point is that I'm trying to prove that P is an H polyhedron, and I'm saying, well, it's a projection of an H polyhedron. And so what I could do is just prove a lemma that if you take an H polyhedron and you project it, it's still an H polyhedron. So all I need to do is, so it suffices to show a lemma that a projection of an H polyhedron is an H polyhedron. Okay. And you should notice that the projections that I'm talking about here are actually very simple projections because they're just knocking off coordinates, right? It's, you're in 5-dimensional space, you knock off the bottom 2 coordinates, and now you live in 3 dimensions. To prove this lemma, actually, it's enough to do a projection where you just lose 1 coordinate, right? Because then you could apply induction. You could project up and knock off 1 coordinate, then knock off another one, then knock off another one. So let me just prove this. Prove when you just take the projection that takes x1 up to xm, and it just forgets what the value of x1 was. I can just prove it for this projection, and then by induction I will have it for any more complicated projection. Okay. And I think what I want to do is instead of writing a bunch of symbols, I'll just show it to you how this works in an example, and you'll see how this is done. Okay. So let's say that I have something like this. So this is my polyhedron, and it's an H polyhedron. It's being given by inequalities. Okay. And I drew it ahead of time, so it looks like this, and like this, and this, and like this. Okay, that's B. And I'm going to project it so that what I'm going to get is this right here. This is the projection that I'm looking for. And what I want to tell you is how to describe this in terms of inequalities. So what I do is the following. I'm going to first look at, so in other words, what I want to do is eliminate x1. Okay? And so what I'm going to do is I'm going to take my inequalities, and I'm going to do 2 things. First, I'm going to consider the ones that don't involve x1, and I'm going to leave those alone. Okay? So this one doesn't involve x1, and I leave it alone. And the other ones, I'm going to just isolate x1 and say either x1 is less than or equal to something, or x1 is bigger than or equal to something. You can always do that, right? So for example, this inequality tells me x1 is bigger than or equal to x2 plus 1. This inequality tells me x1 is less than or equal to 5 minus x2. And this inequality tells me x1 is less than or equal to 3 plus x2. Okay? So now I want to describe proj1 of P, the projection. And what I realized basically is that a value for x2 is possible if and only if there is a solution for x1 to the system of equations. Okay? I want to know if this system of equations can be solved, of inequalities can be solved for x1. When can it be solved? Well, when this is really less than or equal to this, and this is really less than or equal to this. If the lower bounds are all less than the upper bounds, then there are numbers in between that I can put, and there exists a point to project. Otherwise, there isn't. So if I want the description of project 1 of P, all I have to do is take my first inequality that stays alone, that didn't involve x1, and then for each one of these, I just have to say that every lower bound that I have here is less than or equal to every upper bound. And what I have is then my inequality description of the projection, which is what I wanted to show was possible. Okay. Now you'll realize that actually this is not the best possible description, right? Because, for example, this is a very silly inequality to write because it's trivial. So I can forget about this inequality. And then I can say that this is the same thing as saying x2 is bigger than or equal to 0, and 2x2 less than or equal to 6. So x2 less than or equal to 3. Okay. And so the inequality description that I obtained matches my picture, right? These are the points x2 between 0 and 3. If you draw this picture accurately, you'll see that that is really height 3. Okay. So that proves that any projection of an H polyhedron is an H polyhedron, and actually it shows you how to do it. It might not be the most efficient way, but it's a way. And this is what's called Fourier-Motzkin elimination. There is a homework problem about this where I just ask you to carry this very same computation, and this is called Fourier-Motzkin elimination. So that's a bit of hard work, but it gives us our rewards because now we have proved half of our main theorem, which is that every H polyhedron is a V polyhedron. And so in the next class, I'm going to show you why the other direction is true, that any V polyhedron is an H polyhedron. And this is a very valuable tool that you're going to be able to use to prove all kinds of things. Okay? Because it basically means that whenever you want to